So once we have got the expression of voltage and current along the line at any distance s, so next what we can do is, suppose this is my transmission line, and if so for a transmission line at any distance s from the load end, we have got the expression for E and I. And if I take the ratio E divided by I, that I will get the input impedance of the line at that distance. Now, and if the distance is the total length of transmission line, suppose the total length of transmission line is L, then at a distance, that means if I put S equal to L, I will get input impedance at the source end, because this is the end of transmission line. Here transmission line is coming to an end, and here I am having a source. So at source end, that is ZS. So yeah, if we just take the ratio, we get, and if we do slight algebraic manipulation, we get in this form. This one we are just taking the ratio, and we are getting like this as the input impedance of a transmission line. If I take full length L, then it is the impedance at the source end ZS. And if instead of L, if I write S only, then it is just at an arbitrary distance S from the load end, we have the input impedance. Now, another thing that you have to keep in mind is, suppose the value of load is equal to characteristic impedance of the line Z0, which I have already explained before. So when you put this ZR equal to Z0 in this equation, you will see that the what is inside the bracket numerator becomes same as denominator, and you will get the input impedance equal to Z0. That means the line is totally matched. Z is equal to Z0, and in the expression of E and I, if you substitute this ZR equal to Z0, it reduces to only this much, that is equal to ER e to the power gamma S, and I equals to IR e to the power gamma S. So what does this expression indicate? That means at the load end, what value of ER you are having, because ER is the voltage at load end, if you go away, the voltage will keep on increasing. Obviously from source end the voltage will be more. As we go towards load, the voltage will keep on diminishing. So the only point to be noted is the distance from the load end. So we can write E equals to ER e to the power gamma S, or we can write ER equal to ES e to the power minus gamma S. Like this we can write IR equal to IS e to the power minus gamma S. Now this gamma is known as the propagation constant of the wave. Now this propagation constant of the wave, it is a complex quantity. That means it will have a real part which is denoted by alpha, plus j imaginary part which is denoted by beta. Now this alpha is the attenuation constant per unit length. Alpha is known as my attenuation constant per unit length. That means when a wave travels unit distance in a transmission line, how much is the signal attenuated, that means how much the amplitude decreases, that is the attenuation of the wave. That means a wave, the amplitude will go on decreasing because there will be losses in the line. So that is alpha. And beta is the phase constant, that means it is how much the phase of the signal changes when it travels unit distance in a transmission line. The unit of alpha unit is generally written in Nepers per meter. Unit of alpha is Nepers per meter. Neper is Neper. Naper is the unit of alpha attenuation constant. Actually, 1 Naper equal to 8.686 dB. 8.686 dB. That means how much the signal is attenuating, that we can express in dB, and 8.686 dB becomes 1 Naper. This unit you have to remember. And beta is the phase change for unit distance. This is 1 Naper 1, and so beta is radians per meter. Radians per meter, that means when the wave travels unit distance, how much the phase changes, that is radian per meter. So that is how it is getting split. E to the power minus gamma s I can write as alpha plus j beta, and we get like this. Now another point you have to keep in mind is that the relation between beta and lambda. Beta lambda can be written as 2 pi by beta, because beta is how much the phase changes when the wave travels unit distance. Now we know that when the wave travels 1 lambda distance along the length of the line, phase changes 2 pi, because 1 full lambda traveling is equivalent to a phase change of 2 pi. So for unit length distance, phase change is beta. So, or we can say like this, when the wave travels lambda distance, the phase change is 2 pi. And when the wave travels unit distance, the phase change is 2 pi by lambda. And so when the wave travels unit distance, the phase change is 2 pi by lambda. This is only beta, because beta means phase change for unit length. So beta is 2 pi by lambda. So this you have to keep in mind. Now velocity is lambda into f. So 2 pi by beta, we are putting lambda and f. Now 2 pi f is omega. So velocity is omega by beta. That is velocity of propagation along the line is 2 pi by beta. Now we write it in another form. Now how to obtain the expression of alpha and beta, that we'll see in the next video.